Welcome back. In this last lecture, we had introduced the classical dimension analysis using the Buckingham pi theorem. In this lecture, we'll practice on this method by doing some simple examples. The first example discusses the sag of a wire stretched between 2 points, like an electrical conductor of length L between two transmission towers. The sag S will be a function of tension T in the wire, rho the density of the wire, L the length of the wire, and of course on the acceleration due to gravity, because the sag would be because of the weight of the wire, which depends upon G. The first step, we take all the parameters, the dependent parameter S shown in red, and T, rho, L, and G independent uniquity parameters. We use MLT systems of dimension and write the dimensions of these. The density rho is here the density per unit length of the wire. We don't need to worry about the density per unit volume, since the weight would be a function of length. So we work with the density per unit length. So the dimension of rho would be simply mass m1 L minus 1. Tension would be like force, so it would be ml t minus 2. And G, acceleration due to gravity, would have the same dimension as acceleration, and there would be L1 and T minus 2. We take a basic set as T, rho, and L. This basic set makes sure that it is complete and independent. We cannot form a non-dimensional group out of these three. Powers of these three multiplied together will not give you a non-dimensional group. So they are independent. They are complete because from this we can extract the dimension of mass, length, and time. So the value of K here is 3. The value of N was 4, the number of independent parameters. The basic group is 3. K, so the number of independent groups of parameter, non-dimensional parameters they can form would be 1 based on G, and a non-dimensional dependent parameter based on S. S would have a dimension of length. So if we write S as T raised to power alpha, rho raised to power beta, L raised to power gamma, the value of gamma would be 1 and alpha and beta would be 0. So S has the same dimension L. So S by L is dimensionless. And then we have to form the dimensions of G. G, we write T raised to power alpha, rho raised to power beta, and L raised to power gamma in terms of the basic set. G has a dimension of L T minus 2. T has a dimension, tension, T is a tension here, not the time. T is a tension here. Tension has a dimension of M1 L1 T minus 2, ML T minus 2 raised to power alpha. Rho has a dimension ML minus 1 raised to power beta, and the length of the wire raised to power gamma. From this, equating the dimensions of mass on left and right side, we get mass is 0 on the left, mass has a dimension alpha in the first term and beta in the second term. So 0 is equal to alpha plus beta. Then for equating the dimension of length, on the left hand side length is one dimension, On the right hand side, in the first factor, L has a dimension alpha. In the second factor, L has a dimension minus beta. And in third, it has a dimension plus gamma. So 1 should be alpha minus beta plus gamma. Similarly, for time, minus 2 is equal to minus 2a. From these, we can solve the value of alpha, beta, and gamma. Alpha comes out to 1. From this, we get beta is equal to minus 1, and then gamma is equal to minus 1. So that the dimensions of G are T divided by rho L. T1, rho minus 1, L minus 1. So that we can write S by L is a function of only one pi number, G divided by T divided by rho L, or T divided by rho G L. It doesn't matter whether you write inverse or any power of a parameter. A non-dimensional parameter can have any powers. So we used a power of minus 1 here. And so S by L is a function of T divided by rho G L. So it depends only on one parameter. We need to do one experiment. For one wire, we measure T, rho, G, and L, and then obtain the value of S. Once we know this, I can find out what this functional relationship is, and then for any wire with any tension, any material, I can predict the sag. This is the power of dimensional analysis. In fact, this is a power of similitude. Dimensional analysis is only one method of carrying out the similitude. This problem can be solved very easily. It is done in many books on statics, and the result is S by L is rho G L divided by 8T. It is in the same form as a functional relationship we had obtained by dimensional analysis, except that a prime is the function T by rho G L raised to power minus 1, inverse of this. Clearly, the sag should be inversely proportional to the tension in the wire. More the tension, the less is the slag. The factor 8 cannot come from the dimensional analysis. It can be obtained only from experiments or from analytic results. Let's do another example. Time period of vibration of a Nicholson hydrometer. Hydrometer was an instrument used in earlier days to find the density of a liquid. It consists of a weighted cylinder with a long, thin neck of cross-sectional area S. If the liquid were denser, the hydrometer would pop up. If the liquid was less dense, hydrometer would sink more. And this hydrometer was designed so that very small differences in densities could be measured. This oscillated, not something that he wanted it to do, but it did oscillate when he put it in a liquid. The time period of vibrations of the Nicholson hydrometer is given as function of the mass of the hydrometer, the S, the cross-sectional area of the neck where the free surface of the liquid is, rho, the density of the liquid that is there in the jar, and G, the acceleration due to gravity. So the value of N is 4. There are 3 units available if we use MLT system, so that we can write the dimension of the dependent parameter tau and the independent parameter M, S, rho, and G in terms of MLT, and this table gives it. Rho, the dimension of density, is mass per unit volume, ml minus 3. G is like acceleration, L t minus 2. S, the area, is like L square. N is 4. K, the basic set that we choose, is 3. And we choose S, rho, and G as the basic set. These are independent and complete. We can write the dimensions of the remaining quantities tau and m in terms of S, rho, and G, and they themselves do not form a dimensionless group. So the time period tau would have the dimension of S raised to power alpha, rho raised to power beta, and G raised to power gamma. S is L square, so this becomes L square raised to power alpha. Rho is ml minus 3, so this becomes ml minus 3 raised to power beta, and G is Lt raised to power minus 2, so it becomes Lt minus 2 raised to power gamma. And matching the dimensions of m, l, and t, left hand side there are no dimensions of m and l, only t. On the left hand side the dimension of m is only beta in the middle term. For length, the first S contributes 2 alpha, rho contributes minus 3 beta, and G contributes gamma. So the equation is 0 is equal to twice alpha minus 3 beta plus gamma. Similarly for time, 1 on the left hand side, beta minus 2 gamma. From this, we can find out the dimensions of tau as S raised to power 1/4, rho raised to power 0, and G raised to power 1/4. This is for the dependent parameter, and the remaining independent parameter is m. And m, we will find out if we do the same thing, we'll find out the dimension would be S raised to power 3/2 and rho raised to power 1. So that the non-dimensional dependent group is tau G raised to power 1/2 divided by S raised to power 1/4. And that will be a function of m divided by rho times S raised to power 3/2. Doing a few experiments, we can find out what should be the nature of this functional relationship. And once we discover this relationship, we can find out the time period of any hydrometer. Another example, if we take a small pipette and we let a small drop of liquid pendant from this pipette, from the circular orifice of this pipette, you would see the liquid drop something like what's shown in this figure. And this would oscillate in surface tension. The time period of oscillation has to be found out. It can be argued that the frequency of oscillation should be a function of the surface tension of the liquid, the density of the liquid, the diameter d of the orifice, and of course the acceleration due to gravity, because it oscillates under gravity force. So n is equal to 4 in this problem, 4 independent parameters. We choose the MLT system again, quite convenient. We understand the dimension very intuitively, and we write the dimensions for all the quantities, dependent as well as independent, F, sigma, rho, D, and G. You can verify for any one of them. Now we choose a basic set. A basic set would consist of three quantities because M, L, and T are the three quantities. Let's choose sigma, rho, and D. From among the list of independent parameters, we choose three as the basic group so that we write the functional relationship of f and the remaining independent parameters in terms of these dimensions of rho, sigma, and d. Rho, sigma, and d, these yellowed is the basic group. So now we find out by using the same technique as we used before. For example, frequency f is a dimension of t raised to minus 1. Sigma, which is m t minus 2 raised to power alpha. Rho, which is m l minus 3 raised to power beta. And d, which is l length raised to power gamma. From this, we can find out the value of alpha is 1/2, value of beta is minus 1/2, and value of d is minus 3 by 2. So f is sigma raised to power half, rho raised to power minus 1/2, and d raised to power minus 3 by 2 in dimensions. Similarly, we do for the remaining independent parameter g. This would be sigma divided by rho divided by d square. So that the dimensionless equation would be formed out of two dimensionless parameters. The dependent dimensionless group f divided by under root sigma divided by rho d cube, which is sigma raised to power 1/2, rho raised to power minus 1/2, and d raised to power minus 3 by 2. The independent group of parameters is rho g d square by sigma. And therefore, the functional relationship is simply this: f divided by sigma divided by rho d cube under the root is equal to function of rho g d square by sigma. I think you should be convinced by now that it is quite easy to find out the groups that define the functional relationship. Let's do one example in a little bit of more details. Let us consider deformation of an elastic ball striking a wall or a floor. We wish to investigate the deformation that occurs in elastic balls when they impact on a wall. We might be interested, for example, in finding out what determines the diameter d of the circular imprint left on the wall after a freshly dyed ball has rebounded from it. So this ball is traveling towards the wall with the velocity v, elastic ball or diameter capital D. And after hitting the wall and rebounding, it leaves a die spot or diameter lowercase d as shown on the right. Clearly, the diameter of the die spot lowercase d would be a function of the diameter d of the wall, the velocity v just prior to the contact with the wall, the elasticity E of the ball material, the Poisson's ratio nu, and the mass of the ball m. Since we have taken the velocity v just prior to the impact, the gravity effect is not significant. Thus, lowercase d is a function of d, v, e, nu, the Poisson ratio, and m, the mass of the ball. We organize our analysis in this table. The basic group we write as V, M, and D, the velocity, mass, and the diameter capital D of the ball. Velocity at dimension L t minus 1, mass is obviously M, and diameter is L. The other quantities, E and nu in the independent parameters. E has a dimension M, L minus 1, T minus 2. Nu, Poisson ratio, is dimensionless, and D is the dependent parameter. The diameter of imprint left on the wall is length L. So for these three quantities, E, nu, and D, we write in the forms of V raised to power A, M raised to power B, D raised to power C, and find out the value A, B, and C so that the dimensions match. For E, the dimensions would be V raised to power 2, M, D raised to power minus 3. So that E D cube by mv square would be a non-dimensional pi number, non-dimensional independent pi number. Pi 2, the second pi group, refers to nu, which is dimensionless. So this itself is a non-dimensional pi number, nu. No calculation, no analysis needed. And the dependent parameter, non-dimensionalized, is denoted by 0. And clearly, it would have a dimension of V0, M0, and capital D raised to power 1. So that the non-dimensional dependent parameter is lowercase d by capital D. And so, the functional relationship would be something like this. D divided by capital D is a function of E d cube by m v square and nu the Poisson ratio. Usually, this can be written as m divided by d cube, the mass divided by the diameter cube, would be like density, because mass is density times volume, and volume is like d cube. So d cube by m is like 1 over rho. So lowercase d by capital D is a function of E divided by rho v square, where rho is the density of the material. V square is the velocity just before the impact. Sonend, in the text that has been noted as your textbook, gives you data on various experiments done with an elastic ball striking a wall. He used three materials, aluminum, and rubber. The values E, V is given. Each experiments were done with three velocities, and the value of the imprint lowercase d divided by capital E was obtained. These was plotted with these symbols given on the right in this figure. You see that all the points collapse in one curve. In fact, this is quite independent of the Poisson ratio, which is denoted by gamma here. Rather than nu, it is denoted by gamma. We plotted d by d versus E by rho v square. And there is only one line independent of the material, independent of nu, independent of d, independent of E, independent of rho. And this confirms that the analysis that we did is all right. With this single curve, we can predict the imprint diameter for any future experiment with whatever material, whatever size, and whatever velocity we impact a ball with. The imprint diameter can be predicted. Let's do another example where the power of dimension analysis is beautifully on display. The increase in pressure delta P in a centrifugal pump is believed to depend upon the diameter d of its impeller, the density rho of the fluid pump, the RPM n at which the impeller is rotating, and on Q dot, the rate of the volume of the liquid being pumped. Thus, delta P, the increase in pressure, is a function of d rho n Q dot. The value of n here is 4. We'll work in MLT system. As usual, we next write the dimension of all the relevant variables in the chosen system. We determine minimum number r of the dimension required to express these variables. For most problems in fluid mechanics, this number equals 3. MLT is the system that we use. So 3 variables are used. So the 4 independent parameters and the dependent parameter delta L, delta P, the dimensions we have written here in M, L and T system. Their value of R or K is 3 here. So the number of resultant pi numbers would be 2, 1 dependent and 1 independent. The total number of non-dimensional groups of parameters which can be formed by combining the n physical parameters and variables of a problem is equal to n minus r, where r is the number of primary dimensions required to express the dimensional formula of the n physical quantities, the Buckingham pi theorem, which we had stated earlier. Therefore, in this example, we should have 2 non-dimensional numbers, non-dimensional pi's, 1 dependent and 1 independent. For our example, let's choose D, rho and N as the basic groups. This is conventional for centrifugal pumps. We deal in diameter of centrifugal pump, density of the liquid pump and RPM that we operate on. It is now possible to form n minus r independent pi's out of the variable for I from r plus 1 to n, that is from 4 to 5, 2 parameters. And we do the analysis as before. The basic group D, rho and N has a dimension of L, ML minus 3 and T minus 1 respectively. The other groups are delta P, the dependent parameter, which is the dimension of pressure, ML minus 1, T minus 2, force divided by area. Force is ML, T minus 2 divided by area L2. So force divided by area would be ML minus 1, T minus 2. And Q dot, the volume flow rate, would be volume divided by time, L cube T raised to minus 1. So we can form the non-dimensional parameters, D raised to power A, rho raised to power B, N raised to power C. The values A, B and C are determined for the other variables, other parameters. For Q dot, we get value of A as minus 3 and value of C as minus 1. So that Q dot divided by N D cube is a dependent pi number that is formed. This involves a bit of algebra, but it is quite simple. For the dependent parameter delta P, the dimension M, L minus 1, T minus 2 are matched with L raised to power A, ML minus 3 raised to power B, T minus 1 raised to power C. And by matching the dimension, we get the value of A as minus 2, value of B as minus 1 and value of C as minus 2. So that the non-dimensional pi number, dependent pi number, comes out to delta P divided by rho N square T square. I have marked with a rectangle the independent parameter and the other one, pi 1, is the dependent parameter, marked in red. delta P divided by rho n square d square, the pressure developed by the pump is usually expressed in terms of the head H of the fluid, such that delta P is rho GH. So, delta P is replaced by rho GH, where H is the head developed by the pump. Usually, we do not express pressure developed by the pump, we express head developed by the pump. Using this, a non-dimensional dependent parameters becomes like GH divided by n square d square. So, for delta P, I substitute rho GH, and so the dependent parameters becomes GH divided by n square d square. And that is a function of q dot by n d cube. The parameter GH by n square d square is termed as head coefficient in pump engineering, and the parameter q dot divided by nd cube is termed as the flow coefficient CQ, such that CH now is a function of CQ. The dependent non-dimensional parameter is function of only one independent parameter, and of course the geometry of the pump, which we have not written but is understood all through. So, all pumps will have to be geometrically similar. This curve shows the cumulative data for various pumps operating at various speeds and with various flow coefficients. Notice that in this area, for low flow coefficients, for low discharge rate, for relatively low discharge rate, all the curves for different RPMs collapse into one curve. The deviation is only on higher flow rates. What does it indicate? It indicates that our prediction for the performance of pumps is valid for the domain that we considered. The deviation is at higher flow rates when the flow velocities would be larger, and larger flow velocity would lead to cavitation. Since we had not considered the effect of cavitation in our formulation, obviously this was to be expected. The deviation from a single curve, from the predicted curve, is only where the cavitation is suspected. And we don't operate our pumps in this region because of the damage that the cavitation and the resultant collapse of vapor bubbles results in the impeller. Let's do one more example. In this example, we take two body orbits. Two bodies are orbiting under the influence of the gravitation force between them. The force of gravity is given by G times m1 m2 divided by r square, where r is the distance between the two, m1 and m2 are the masses of the two bodies, and G is the universal gravitational constant. So, time period tau of the circular orbits would be a function of m1, m2, r, and g. We construct the table showing the dimensions. In MLT system, tau, the independent parameter, is written in red, m1, m2, r, and g. The dimensions are easy to verify. The dimension of g, the universal gravitational constant, is obtained from this equation of the gravitational force. We use m1, r, and g as the basic set, And we do this, the dimension of T comes out to be m1 raised to the power 1 half, r raised to the power minus 1 half, and g raised to the power minus 3 by 2. And of course, the dimension of m2 would be simply m1. m2 by m1 is dimensionless. So that the two parameters, the dependent pi number would be tau into m1g by r cube raised to the power 1 half and m2 by m1. The first one would be the function of the second one. We can manipulate this to write tau square. The time period would be like r cube divided by m1g in function of m2 by m1. Santiago has plotted the orbital time period or the square of the orbital time period tau square against the cube of the semi-major axis in astronomical units for the solar system. The third one from the left is our Earth. So these are the planets of the solar system. They are on one line as was expected, using the mass of the system. Let's do a little mathematics. Tau square is this. Since it should not matter as what we call body 1 and body 2, so that by symmetry, r cube divided by m1g function of m2 by m1 should be like r cube divided by m2g function of m1 by m2, reversing the role of m1 and m2. And if we do this, we get function of m2 by m1 should be equal to m1 by m2 into function m1 by m2. That is, fx is like 1 over x, f of 1 over x. One solution of this functional equation is if fx is like c divided by 1 plus x. C divided by 1 plus x satisfies this functional equation. And so that tau square, the time period of the planetary motion, can be written as some constant time r cube divided by g times m1 plus m2. This is the Kepler's third law of planetary motion, obtained without much algebra, without understanding dynamics completely, without solving complex equations, which Kepler did. So we are able to obtain solutions. This is the power of dimensional analysis. Thank you.